Hello. In this work, we focus on hydrogen diffusion modeling in Abaqus and demonstrate how the same framework can be applied to predict hydrogen-assisted fatigue. This work is based on ACTA publication. Hydrogen diffusion is a key mechanism underlying hydrogen embrittlement in high-strength steels, especially under cyclic loading conditions. This approach is based on a fully coupled stress diffusion formulation, capturing lattice and trapped hydrogen concentration, microstructural trapping. For example, hydrogen can be trapped in the grain boundaries, carbides, and dislocations, and also crack tip plasticity effects under cyclic loading. The numerical implementation combines UMAT, UMAT+HT, and UEL subroutines into a robust Abaqus architecture suitable for both research and industrial applications. Using this framework, you can directly predict lattice and trapped hydrogen concentrations, frequency-dependent hydrogen accumulation, and identify safe and unsafe fatigue regimes in hydrogen environments. What you will learn and access after this video. In this video, you will first understand the physical mechanism behind multi-trap hydrogen transport and how cyclic loading competes with diffusion and crack tip plasticity. Then we move into a numerical implementation, showing a full Abaqus workflow under cyclic diffusion condition and crack tip modeling. Then we will validate the framework against experimental fatigue data and demonstrate how trap density modifies safe operations regimes. Finally, you will gain access to full Abaqus project files, UMAT UEL UMATH source code subroutines, the Fortran codes. You will get step-by-step tutorial videos explaining all Abaqus models step-by-step and subroutines line by line, and you can have a custom hydrogen project support. Mechanism. Let's talk about the mechanism behind these things. At crack tip, we have hydrostatic stress concentration. This stress concentration produces plastic deformation. Plastic deformation means dislocation generations, especially at lower temperature, These generated dislocations, are places for hydrogens to move, to diffuse. Hydrogen can lock dislocations, and this can reduce plasticity. Reduced plasticity at crack tip can limit the crack tip blunting, and it will increase crack propagation rate. And finally, we will see decreased fatigue life. But in this mechanism, the most important is hydrogen diffusion into the dislocations, or let's say into the microstructural traps. This hydrogen diffusion is time dependent. It's very important how fast a hydrogen atom can move. If diffusion speed greater than loading frequency in cyclic loading, then it means that hydrogen atoms actually have enough time to diffuse and into the dislocations and actually lock the dislocation. So this will actually conclude in significant crack tip accumulation. So we will have hydrogen embrittlement. But if we have a actually large loading frequencies, big loading frequencies greater than diffusion speed, then we will have limited hydrogen buildup. So we will see no hydrogen effect. So this mechanism is telling us that fatigue behavior depends on the ratio of dE per F frequency. dE is diffusion coefficient, the effective diffusion coefficient, and loading frequency. For example, look at this experimental data from an ACTA paper. The blue points are the crack propagation rate of raw material without hydrogen without hydrogen atoms. The blue points. You can see that if the cyclic loading frequency is big, so very large value, then we will not have any hydrogen effect at high frequencies. But in low frequencies, then we will see increased crack propagation rate and decreased fatigue life. This is the hydrogen effect. These experimental beautiful results can help us to understand the beyond mechanisms under hydrogen effects. Let's talk about formulation and solution. Total dissolved hydrogen into the material can be decomposed to two parts: lattice hydrogen. The part of hydrogen atoms can move freely through the lattice, and trapping hydrogens trapped in microstructural defects. So first let's talk about diffusion equation, mass conservation, or Fick's law. Fick's law, yes. So in the mass conservation or diffusion equation, the lattice hydrogen concentration and trapped hydrogen concentration is in a relation between effective diffusion coefficient and hydrostatic stress. This is very important, that stress can affect on hydrogen diffusion. And also the trapping sites, the microstructure defects, can affect the diffusion. So this is not diffusion equation, this is diffusion coefficient, this is effective diffusion coefficient. So this effective diffusion coefficient actually is a function of diffusion coefficient, and here we have a trap site density. How many trapping sites we have, how many dislocations, how many grain boundaries, how many carbides. So to compute this actually trapping site density, actually after computing the effective D, we can have this value, this actually number, which is dE per F, the loading frequency, and we can decide safe and unsafe fatigue regime by this parameter. But if we want to compute, I was telling you, if we want to compute trapping density, we have a very well-known equation, which is Oriani relation. It relates the trapping density to lattice sites. So we have a lattice sites, we have a binding energy coefficient, and we can compute trapping site density and put it here, compute dE, use dE for safe and unsafe regimes, and then use dE here, compute this hydrostatic stress from UMAT, and after that compute the hydrogen concentrations. It's a actually big formulation and solution. It's being solved in UMAT UEL and UMAT+HT subroutines. A complete formulation, explanation, numerical solution, the subroutines, and Abaqus implementations are provided in the tutorial package at the end of this video. Workflow, Abaqus implementation. It is a coupled distress diffusion architecture. So fully coupled mechanical and hydrogen diffusion problem. And we will have transient cyclic loading with time-dependent diffusion and crack tip boundary layer formulation. For example, in this video, we are working on this example. We have axisymmetric crack here. Here, the hydrogen diffusion at the beginning of the simulation is 0. We are applying displacement to this boundary, and we are charging the hydrogen from this boundary. And we want to see how this hydrogen is going to diffuse to the crack tip and affect the fatigue of this sample. So let's talk about subroutine structure. UMAT. We use UMAT for mechanical response and crack tip plasticity. To compute all these things, we need hydrostatic stress and plastic strains. These are coming from UMAT. And dislocation-based trap evolution is also in UMAT. Then we need to solve diffusion equations. We use UMAT+HT for that. It is stress-assisted hydrogen diffusion and multi-trap transport. And we need to transfer parameters between UMAT and UMAT+HT. We use UEL for that. So stress diffusion parameters transfer between UMAT and UMAT+HT by UEL subroutine. All of these subroutines are explained. A complete Abaqus projects and subroutines again provided in the tutorial package you can see at the end of this video. Results. Let's have a look on the results. This is a good comparison between of our present model results and an experiment result. First, let's have a look on the green points. Total hydrogen concentration. It is in agreement on the total hydrogen concentration between the model and the experiment. Then let's have a look on the blue points. Blue points are lattice hydrogen concentration. The hydrogen atoms can move freely into the lattice. So it is a very good agreement between our model results and experiment. Then look at the pink points. You can see an agreement between the model results and experiments for actually trapped hydrogens into the carbides. The amount of hydrogen atoms trapped into the carbides. And also the agreement between the trapped hydrogens into the dislocations. The amount of hydrogen atoms trapped into dislocations. There is a very good agreement between the model and experiment. And by these hydrogen concentrations, we can actually define and design the embrittlement and non-embrittlement unsafe and safe fatigue regimes like this one. Implications. Engineering implications of the framework. You can use it for frequency dependent risk assessment, identify critical loading frequency ranges, identify and predict safe and unsafe fatigue regimes, and evaluate service conditions under hydrogen environment. It can be used also for microstructural designing and optimization, and assess influence of trap density and binding energy, study carbide dislocation trap engineering strategies, and design alloys for extended fatigue life. Also, it can be used for simulation-driven development. You can use this model to reduce experimental efforts and experimental costs, perform parametric studies efficiently, and accelerate hydrogen fatigue assessments in Abaqus. So hydrogen diffusion modeling enables predictive hydrogen-assisted fatigue design. But how? It is challenging, but don't worry, we simplify it for you. The challenges, the difficulties. The first one is limited documentation. You cannot find many documentation about how to model hydrogen diffusion in Abaqus. It's limited. And we have complex Abaqus setup. complex UMAT UEL UMATH coding and subroutines, mesh refinement due to crack and fatigue design, and there is no built-in hydrogen model in Abaqus. These difficulties, actually, these are challenging in the hydrogen modeling in Abaqus. But we have made it very simple, so you can learn it easily and quickly. The first strategy, use our tutorial package. Learn the complete workflow, all the subroutines and Abaqus models, and apply it to your own project. Or you can request a custom Abaqus hydrogen project. You can save your energy and time. We will complete your project. We will produce your desired results and teach it to you by tutorial videos and online meetings. Let's talk about tutorial packets. The package number 1 is Diffusion Fatigue package. So it is hydrogen assisted fatigue modeling. What is included? You will get comprehensive tutorial videos explaining the theory and formulation, all details. The video will explain Abaqus models step by step. The UMAT UEL UMATH subroutines will be, it is explained in the tutorial videos line by line. So, and result extraction and interpretation. And everything explanation is actually makes this package ready to adopt for your own project. Again, I'm emphasizing that you don't need to know many knowledge and to know many things about Abaqus and subroutines. Everything is explained step by step and line by line. Also, you will get complete Abaqus project files. All Abaqus files, input files, CAE files, and all other files. UMAT UEL UMATH Fortran source files, documentation PDF and PPT training files, and you can download this package by the link in the description. This is the first package. But let's look part 2 package, the second package, which is hydrogen induced damage and cracking. In the previous package, we didn't have damage and cracking due to hydrogen. But in this package, you can see crack initiation and propagation actually induced by hydrogen driven degradation law, and Coop diffusion damage mechanism. And you will see progressive failure simulation. So here we have damage and cracking induced by hydrogen. Again, you can get the download link in the description. The package number 3, the part 3, it is 3D hydrogen diffusion fatigue and cracking. The previous packages were in 2-dimensional. Here we have a full 3D component modeling. We have 3D diffusion, 3D cracking, 3D damage, 3D fatigue, and real geometrical implementation. So it is industrial scale simulations. So you will have full diffusion fatigue and damage framework here in 3-dimensional. So these 3 packages are very useful and complete to help you to learn all the things. Again, the download link in the description. But if you have a custom Abaqus hydrogen project, you can order it. You provide your project details. We will get your details and we will provide a tutorial package. We will produce your desired results and actually deliver to you. We will receive details and produce your project package. All Abaqus models, user subroutines, tutorial videos, extracted results, and PDF and presentation training files. Thank you for your attention. If you have any question, you can actually contact us. We will help you in your hydrogen projects. Thank you again for your attention.